So we go back to the IP layer. The IP layer is in principle unicast. You send a packet to an IP address. However, in the 90s, beginning of the 90s, people invented IP Multicast, and the goal was, as illustrated not on this, but on the previous slide, the goal was to serve radio and TV broadcasts over the internet. You can see things like today, if you listen to internet radio, you probably don't use multicast, except if you listen to your Swisscom TV that also provides a radio channel. This one uses multicast. But if you listen to radio live on the internet, it's sent in unicast mode to you, which means there are huge servers that serve for popular radio or TV channel millions of customers. Those servers cost a lot, and small radio programs like this one, for example, may have problems, and they don't want to pay large capacities, so that their internet presence might be limited. Multicast is a radical cure to that, where the idea is that the IP packets can be sent to a large group, small or large group of destinations. So if you are a radio or TV channel and you're broadcasting live on the internet, you send only one packet. So your server, your broadcast server, needs to send only one packet, as if you would be sending to one destination, compared to 1 million packets when you're sending to 1 million destination with unicast. That's the purpose. For this, in IP addressing schemes, both IPv4 and IPv6, there is a reserved set of addresses that are multicast. For IPv6, it's very simple. It's FF00/8. That means anything that starts with FF means multicast. In IPv4, it's the block 224 and above. A multicast address is very, very different from a standard IP address. It has nothing to do. It's a radically different thing. It's a logical group identifier. It has no topological information. IP addresses have topological and organizational information. For example, 128, 178. We know this is an address that's allocated to EPFL, and we can guess where EPFL is in the world, so we have a lot of information on how to send packets to such an address. Multicast is different. Multicast is just a group number. So if you listen to a TV channel, then you would need an IP multicast address for this channel, for example. The downside of it is that routers need to know how to distribute this information, and if listeners come and go, this information is dynamic. So it's not static information or quasi-static information like routing information. It's really information on who is listening to this group, which is a radical change. I mean, routers are in principle not performing stateful operation. Stateful means if I send information from a web server to a client, the routers on the path have no special information, no state information that is relative to that transfer. The only information they have is the routing information, but this is general information. And if there is no change in the topology, for example, on the EPFL campus, when there is no failure or no addition or removal of a node, this information does not change. So we say that the IP layer is stateless or connectionless. In contrast here, IP multicast makes the routers connection-oriented and stateful. So it's a radical change for a router to be IP multicast. A member of a group is, in fact, the listeners. Here is in one slide how it works. I'm showing on the right a server S, so think of it as a Swisscom TV server sending a football match live, for example. Then the server simply sends to a multicast address, M. The address needs to be allocated for this special channel. And then, like any ordinary IP packet. It goes to the default router. Now, if nobody's listening, that's the end of the story. If nobody's listening to the group, then routers will not know how to transfer this packet, so they will drop it. So you're sending and nobody's listening. It's really, it's hopeless. I mean, it's a very stressed situation, but this is how it works. Now, if somebody's listening, which is likely, then the listeners have to actively do something for the network to change its state to compute a distribution tree. And this is called joining the group. In IPv4, it's called IGMP, Internet Group Management Protocol. In IPv6, for some reason that is probably bad, it has a different name. It's called the Multicast Listener Discovery, but it's the same. It just means that A wants to listen. That means somebody at A has clicked on a web link somewhere saying, listen to this program. So by listening, that means you start a socket that tries to receive the data that have destination address M. When you do this, your operating system will send an IGMP message to all multicast routers on link with you. So to all routers that are on the same local area network as you and support multicast. If you're on the Wi-Fi of EPFL, that set is empty. There is no multicast-enabled router on the multicast of EPFL. If you are on the Wi-Fi of the TCP-IP labs, we have multicast routers. So there you will find some multicast router. Most of the time, the multicast router is your default router where multicast is enabled. So at point 2, this message will be received by router 1. And what will router 1 do? Well, router 1 will keep some state information illustrated by the red box. That means router 1 will remember, oh, I have somebody on my left port that is listening to address M. Now I need to find a way to get the data to M. So how can I do that? Well, this is building the multicast tree. There are zillions of protocols that are used for building the multicast tree, but the simplest of all, which is also one that is frequently deployed, consists in doing reversed shortest path routing. So the way it would be done here is R1, when we do a join, if we have in addition some information about the source. For example, here, if we do what is called source-specific multicast, so we know we want to join a group M, but in the join we add some information, and here is the IP address of the source, so the machine S. If that information is present, then the job of multicast routing is fairly simple. You will simply forward a control message, a multicast routing protocol packet, in the internet towards the direction of the source, which is what happens here. 3, R1 sends a packet towards S, and it goes to router R2. Now router R2 receives that message. That's more or less the same as a join message. It is saying somebody in this direction would like to receive M. R2 will do the same and will forward a packet to R5, and now R5 knows that S is on its local port. So R5 knows now whenever it receives an IP packet with destination address M, and perhaps if we do source-specific multicast with source address S, then I need to copy it and forward it to router R2. To whom I should forward it is in the red box. I need in this red box to have information on which ports I need to forward it to. If things are multicast, then of course what will happen is the following packet will now reach the destination A, and A will be happy. Of course, if you do multicast things, you assume that you will have more than one receiver, so sooner or later somebody else, like B, will join. The same process will be applied, and now the difference is that when router R4 sends the join message to R2, or the multicast routing protocol join to R2, then there is a merge of the different branches of the distribution tree. So the process will stop at R2. R5 will not be involved. The only thing that we need to add is in R2 another entry in the table saying every packet that is destined to address M needs to be duplicated by R2. Now it is R2, in this case, is the only place where a packet will be duplicated. So a packet that is now sent by S will be forwarded by R5 to R2. R2 will duplicate it, and R1, R4 will send them over the local area network, perhaps in broadcast mode, perhaps in other modes, to the final destination. This is how multicast works. So we see that the main idea of multicast is that the packet duplication is done by the routers. And the idea is that if you have a large network, you probably have a large number of hops, so perhaps you have 20 hops on your way. If you have 20 hops and every router duplicates a packet only once, which is a small job for a router, instead of copying on one output, you copy it on two outputs, then you will have 2 to the power 20 packets replicate, which is 1 million. So instead of having a source sending 1 million packets, if you have a path that is at a depth of 20 and everybody duplicates it once, then you can reach 1 million destinations. Of course, this is a bit highly theoretical. That assumes things are perfectly well balanced so that the tree is a perfect tree. In reality, trees are much less balanced, but that's the idea. The idea is that routers duplicate packets. The worst case, they have to duplicate an input to all outputs, but routers don't have millions of outputs. They have perhaps 1,000 outputs in the worst case. So a router needs to duplicate a packet a relatively small number of times. If this is done enough times, then we reach those millions or hundreds of millions of packet duplication at relatively low complexity. That's the theory, that's the idea. Of course, in practice, this is interesting only if you really have a multicast service. Multicast service means everybody's interested in receiving the same thing at the same time. And what people have not envisioned in the at the beginning of the 90s when this was done is that eventually TV becomes something different, where you watch TV on YouTube, and then if you stop to go to the bathroom, then you simply stop and come back later. But the fact that you stop means you're not listening or receiving the information at the same time as others. So most video and audio transmission on the internet is in fact asynchronous, is not strictly synchronous. So this is for events, for football matches, for a few things like this. It is also widely used in a completely different setting that was not envisioned by the founders of IP Multicast, which is in industrial environments. If you have machines like sensors that send information to servers that receive it, then the so-called servers are typically sent, the sensors typically send to a multicast address. So that the benefit of that is that the sensors that are relatively simple devices don't need to be worried to whom they send their data. So they send it to a group. Now, if there is one receiver or several receivers, as is traditionally the case, then you don't need to modify the codes of the sensors. So this is, I would say, the most widespread application today, apart from real-time TV distribution. We have seen already when we talked about layer 2 and bridges that the layer 2 also can sometimes handle multicast. There is no ARP with a multicast, so if we send to a group address, an IP group address, the MAC destination address is algorithmically derived from the group address using one of those two clumsy algorithms with the details that are given in these slides. Now, how is that done in practice? On the top, you have non-smart switches, and non-smart switches simply send a broadcast packet to everyone. So if a MAC destination address is a multicast packet, the packet will be sent by everyone, and then the systems that don't listen to it will, in principle, if they're not cheating, if they're not spying on the traffic, will drop it. Now, if you send multicast traffic, it means probably you assume that anybody can receive this traffic. If you want your communication to be secure, which you probably do, you have to have a security mechanism that can live with the fact that anybody can receive your data. So typically, if you want the data to be secret, you have to encrypt it. Smarter switches, like the Cisco switches we have at EPFL on the wired network, will build a distribution tree very much like the routers do. In fact, the switches are often co-located with the routers, so they can simply imitate what the routers do and build a similar a similar distribution tree. As I mentioned, a major drawback of the multicast is that it forces the routers to do things that we would not like them to do. So whenever an IP router has IP multicast enabled, whenever it receives an IP packet with a destination address that is of the multicast type, so deciding whether the address is multicast or not is a fairly simple thing that is typically done in high-performance routers by hardware assistants. Then this packet needs to be forwarded by looking at an exact matching table that is given by the tree, in the best case. In the worst case, it needs to be dropped because the distribution tree is not yet being completed. And of course, there is no possible aggregation. For example, we see here a case where one of the receivers is receiving M1 and M2, and two other guys are receiving only M2. There is no way in router R1 to aggregate the addresses M1 and M2, for example. You have a completely different distribution tree for each of the addresses. In practice, IP multicast is, as I said, supported in special environments. So if you have Swisscom or Sunrise TV at home, and if you can do a Wireshark on your devices, you will see that there is IP multicast in the TV distribution channels. That's I would say, one of the domestic use of IP multicast. But most interests of multicast are for sensor, Internet of Things type of applications, where you can statically encode the destination of data for a sensor, for example, without having to worry on whom will receive it. Multicast poses a number of problems. This is why many network operators are very, very cautious about multicast. What kind of problems could you imagine it can cause? Yes, you could easily, so the problem is the denial of service attacks. You can very easily create very large amounts of traffic with multicast. So if you find a way to send, to manipulate some of the joins, or to send packets that have IP multicast addresses that have enough robots in the world that are listening to them, then you can create a lot of traffic with relatively little work for the sender, at least. So for this reason, probably, many operators are very, very careful and typically don't allow it. That's the case of EPFL on the Wi-Fi EPFL network. At EPFL, it's enabled on the wired network. So if you connect to an Ethernet port, multicast support is enabled, but for some reason not on Wi-Fi. So we conclude this okay, so I see there's lots of interesting I close in 5 seconds. And the majority vote is the correct answer. So this, whoops. This and that are true, which means B and C, which is F. Voilà, that's all we will say about multicast today. There's another quiz, but I'll let you discover, test it, and see the answer when later today when I post the solutions. What we have not seen is multicast routing. We will not see it in the lecture. Perhaps it's something we could do in a research exercise 1 year. IP Multicast requires the deployment of a solution for routers to compute multicast distribution trees, which is very easy to do with what I mentioned is called source-specific multicast. So among the multicast addresses, there is a small group of them that are said to be source-specific. That means the true label of the group is the combination of the source address and the multicast address. So if you join to a multicast address, you have also to say, I join to this source and to this multicast. With this form of multicast, it's very easy to build distribution trees because you know where the source, who the source is. With a general multicast, which is the one that is by default standard in the internet, anybody can send to the multicast destination address. So you don't need to be a specific source to send. So it's what is called a closed user, an open group, where anybody, by simply sending to that address, can create traffic. Of course, that poses a number of security concerns, as we have discussed already. Voila, that's the end of multicast, at least for us today, but it will continue in the lab.